in my former university, China University of Petroleum, Beijing. And my talk here, I talked about this technology here a lot for advertising, just to show you how technology is developed from laboratory to final industrial application. And I will divide my presentation into the following 4 parts. To begin with, I'd like to say something about the background. In recent years, bad forecast has weather frequently comes down to China. This picture shows you how Beijing was like in haze and forecast. And this is the Port Lesser and the West Railway Station. And it has been found that the vehicle exhaust emission has become one of the important sources of air pollution, and its contribution to the forecast hazard is estimated to be 22%. So to control the air pollution caused by petrol-powered vehicles, the Chinese government has, speeded pace to update its regulation on gasoline and diesel. And according to the Ministry of Environment Protection, the China 4 standard, that is equivalent to Euro 4, has been enacted in 2014, and the China 5 will be enacted in the next year, and the sulfur content should be below 10 ppm, and the olefin content of gasoline should be below 24%. And the China 6, that is almost equivalent to Euro 6, will be enacted in 2017. And the main trend for Chinese refinery to upgrade the vehicle petrol standard is to lower the olefin and the sulfur content. However, in China, in the commercial gasoline pool, the FCC LAFSA takes share of at least 7%. As we know, the sulfur content, your typical FCC LAFSA is usually between 200 to 2,000 ppm, which is much higher than the regulations. And the olefin content is usually between at about 40%. So the key for Chinese refineries to produce clean petrol is to decrease sulfur and olefin content of FCC LAFSA. The main challenges we are facing is that currently, to meet the requirements for producing China 5, China 4, China 5 standard blending components, we must deeply hydrosulfurize FCC LAFSA. But deep HDS will naturally cause the saturation of olefins that have very high octane ratings. So the first challenge is we are facing is to decrease the sulfur content. And the second challenge is that currently the HDS technology mainly focus on HDS rather than olefin deduction. But the standard requires to decrease the olefin content. But olefin reduction will naturally give rise to serious loss in octane ratings. So how to decrease olefin content without causing octane loss in gasoline is another challenge. So an ideal process should be trifunctional. That is, it must meet the requirements for deep desulfurization, significant olefin reduction, and good octane preservation. So for this purpose, in the China University of Petroleum, we developed a process called the GARDES process. In this process, the full range FCC gasoline to be treated is first pre-hydrogenate in this reactor, and then the treated full range FCC LAFSA goes into a distillation column. Here, we split the full range FCC LAFSA into 2 fractions. One is light FCC LAFSA. This fraction has very low sulfur content, but very high olefin content. And a heavy FCC fraction this fraction has very high sulfur content, but very low olefin content. So this stream should be first deeply hydrodesulfurized and then goes into another reactor called octane recovery reactor. Here we convert olefin into isoparaffins and aromatics that have very high octane ratings. And finally, we recombine the net FCC levisa and the treated heavy FCC levisa into one stream for blending, okay? So in this process, the catalysts play a key role to assure the success of the process. So my talk will mainly concentrate on the catalyst development we have made in the China University of Petroleum. And the first question you may ask is that why we split the full-range FCC levisa into two fractions. This is because in the lead fraction with its boiling point below 60 degrees, the lead fraction contains about 60% of the olefins, but only 3% of the sulfur. So if we directly treat the full-range FCC levisa, this will give rise to serious loss in octane rating of the FCC levisa because the serious saturation of olefins. So a suitable way to avoid olefin saturation is to split the full-range FCC levisa into a light and heavy fraction in which the light fraction must be sweetened before being blended into final products. By analyzing the distribution of olefins and sulfur-containing compounds, we found that the main sulfur-containing compounds in that fraction are mercaptans. So we can make use of the addition reaction between mercaptans and olefins in FCC levisa to transform mercaptans into heavy sulfide. So this is the addition reaction between mercaptan and the diolefins in the FCC levisa, and then they combine to form a heavy disulfide. So this is SCD spectrum of the feedstock, and this is the SCD spectrum of the pre-hydrogenated product. You see, these peaks existing in the feedstock completely disappear. Means that the lead mercaptans have been transformed into some heavy disulfide. So after splitting, this heavy sulfide can be divided into the heavy fraction, and this is the results we obtained of our catalyst we developed in the laboratory. You see, when taking Doosan's FCC levisa as the feedstock, you see we achieve the mercaptan conversion at 72%, and the olefin reduction is just 0.35. So means the catalyst has very high selectivity. And after finishing the laboratory study, we established 250 kTIM per year per hydrogenation units in Harbin refinery, and after 50 days running, we made process rating. This is the process rating conditions, and this is process rating results. You see, we got a mercaptan removal ratio as high as 96%, and the olefin conversion is also as high as 97%. The second catalyst I'm going to talk is the HDS catalyst. As we know, in a typical HDS catalyst, both the hydrogenation of olefins and the hydrodesulfurization of sulfur compounds may take place simultaneously on the metal sulfide particles. But the rim side, that is the white area, the rim side at the top and the bottom section of of the metal sulfide can catalyze both hydrogenation and HDS reaction, but the HSide can only catalyze HDS reaction. So to improve the selectivity of the catalyst, we must increase the stacking of the metal sulfide. But let's decrease the HDS activity. But if we decrease the stacking of the metal sulfides, we increase the activity, but lower the selectivity. So to achieve higher selectivity and activity, we must have a compromised stacking and dispersion of the metal sulfide. So this picture shows how the selectivity and activity change with the morphologies, that is dispersion and stacking of metal sulfides. According to these results, we finally developed a highly selective HDS catalyst. This gives the results. When we use a feedstock containing 700 ppm sulfur, we got a selectivity about 78%. And the third catalyst is the octane recovery catalyst. The best way to decrease olefin content without causing series loss in the octane rating, the best way is to transform olefins in FCC into monobranch isomers or 2 or 3 branched isomers, while depressing the saturation of olefins. So for this purpose, the catalyst should have very high, suitable acidity and pore size to provide isomerization and aromatization activity. So we develop a combined steaming and volcanic acid treatment method to adjust the xylate HZN5 acidity and pore structure. And finally, we developed a catalyst. You see, when the olefin content decreased from 40% to 21.5%, the octane loss is just 0.5. It's satisfactory. And but you see, the HDS performance is not so good. So finally, we combine the 3 catalysts we have developed into a process. That is this process. In the first reactor, we load the pre-hydrogenation catalyst. In the second reactor, we load HDS catalyst. And the third one, we load the octane recovery catalyst. For this process, very satisfactory results were obtained. You see, when the first reactor is operated at 120 degrees C and 2.2 MBAR, and the second reactor operated at 220 degrees C and 1.5 MBAR, and the third reactor operated at 320 degrees C and 1.5 MBAR with hydrogen to oil ratio of 300. We got the following results. The olefin content was decreased from about 40% to 24%, and the sulfur content decreased from about 357 ppm to 14 ppm, and we got increased our own number. So after finishing the laboratory test, we built 200 kton per year industrial units, and this unit was successfully run for about 20 months, and finally we developed a process package, and now we have successfully erected 15 industrial units and issued 6 licenses have been issued. The total capacity has exceeded 11 million tons per year. And because of the limited time, I'm not able to show the process rating results of the different units. And this is the summary of the industrial application of the GARDES processes we have developed until now. And this is the 6 license we have issued to the domestic and foreign refineries. And this picture shows you the milestone we have experienced in the process of the technology development. You see, from 2001, we began to develop this technology, and we spent about 80 years to finish the catalyst and the process development, but it will take another 80 years for commercialization. So it's a long story from about 2000 to 2015. So 15 years, just told by Professor Chanaleni this morning, a long story. So the lessons we have learned can be summarized as follows. Even at the very beginning of the catalyst development, the catalyst preparation scale should be at a kilogram scale. That's very important. If you use just maybe 1 gram or 2 gram, no useful. So, and the preparation at gram level provides no help. And the second lesson we have learned, the raw materials used must be identical to those used in industrial manufacture. And the third, the catalytic assessment should be conducted in 100 milliliter vanadium reactors. Otherwise, the results are unreliable. And the feedstock should be industrial wise. I have discussed with Professor Chanaleni this morning. And the fourth, commercial and manufacturing technology of HLS catalysts are very mature. The accomplishment of 100 milliliter assessment test naturally is an indicator of future commercialization. And finally, the conclusion. Upgrading FCC gasoline with higher sulfur and olefin content is challenging Asia refineries that take FCC lifestyle as the main petrol blending component. The GARDES process combines highly selective hydrodesulfurization and directed olefin conversion, and thus on the abilities of deeply reducing sulfur content, significantly lowering olefin content, and satisfactorily preserving octane rating, demonstrating itself as an important route for hydro-upgrading FCC lifestyle with high sulfur and olefin content. The GARDES process has been widely used in Chinese refineries to produce China 4 and China 5 standard clean petrol, with 15 units being erected and 5 licenses being issued. We hope the GARDES process can be useful in Thailand and other countries, and some Asian countries. And finally, I should thank the support from the Ministry of Science and Technology of China, National Natural Science Foundation of China, and the China National Petroleum Corporation, and so on. Thank you for attention.